As part of actualizing quantum computation, today we shall discuss the phenomena of quantum jumps. Quantum physics measurements can fundamentally yield discrete and random results. God does not play dice syndrome that always annoyed Einstein but cannot be helped because nature is quantum in nature. The right-hand side of this slide shows the Bohr model of the hydrogen atom, and it also indicates the well-known Lyman-Balmer-Paschen bracket and Fund series. The emission and absorption spectra, frequency, the region in which these spectra occur are also indicated. In 1913, Bohr proposed quantum jumps between two discrete energy levels of an atom, and this formed the bedrock of the so-called semi-classical description of the hydrogen atom. Experimentally, quantum jumps were first observed by Nagorny et al. In 1986 in an atomic ion driven by a weak deterministic force while under strong continuous energy measurements. The times at which the discontinuous jump transitions occur are reputed to be fundamentally unpredictable. Despite the non-deterministic character of quantum physics, is it possible to know if a quantum jump is about to occur? On the right-hand side, there is a photograph taken by Scott Eklund, and it shows physicists John Cramer to the left and Warren Nagorny work in the lab. Nagorny says he has a faint understanding of Cramer's idea. This particular photograph was taken on 15th November 2006. Nagorny et al. Demonstrated the direct observation of quantum jumps between the 6 2s half state and the 5 2d 5 half state of an individual laser-cooled barium ion contained in a radio frequency trap. The state detection and cooling were performed by two lasers which cause 6 2s half to 6 2p half to 5 to 3d half transitions. Incoherent excitation to the 5 2d 3 half state via the 6 2p 3 half level caused the fluorescence from the 6 2p half state to be suppressed for a time greater than 30 seconds, which is the lifetime of that state, after which the fluorescence reappeared. The resulting telegraph signal provided a direct monitor of the atomic state. This slide simply shows a larger picture shown before in the third slide of John Cramer and Warren Nagorny at work in the lab. Fluorescence and phosphorescence. Fluorescence is one of two kinds of emission of light by a substance that has absorbed light or other electromagnetic radiation. When exposed to ultraviolet radiation, many substances will glow or fluoresce with colored visible light. The color of the light emitted depends on the chemical composition of the substance. Fluorescent materials generally cease to glow nearly immediately when the radiation source stops. This distinguishes them from the other type of light emission, phosphorescence. Phosphorescent materials continue to emit light for some time after the radiation stops. Here, one can see two different kinds of fluorescence. On the left, marine, that is natural in nature, and on the right, various different types of crystals which have been shone on with ultraviolet light, and then they tend to emit the radiation back. In this particular picture, we can see Zlatko Minev and Michel Devore in front of their experiment. This photograph is courtesy Yale University. Minev and Devore experimentally demonstrate that the jump from the ground to an excited state of a superconducting artificial three-level atom can be tracked as it follows a predictable flight by monitoring the population of an auxiliary energy level coupled to the ground state. Experimental results demonstrate that the evolution of each completed jump is continuous, coherent, and deterministic. They exploited these features using real-time monitoring and feedback to catch and reverse quantum jumps mid-flight, thus deterministically preventing their completion. These findings, which agree with theoretical predictions, essentially without adjustable parameters, support the modern quantum trajectory theory and should provide new ground for the exploration of real-time intervention techniques in the control of quantum systems, such as the early detection of error syndromes in quantum error correction. More on quantum trajectory theory and quantum error correction codes in the next two videos. Till then, have fun and enjoy quantum computation.